Yeah. So, welcome back to the part 2 of fluid flow modeling, and we will continue from where we left over in the part 1. And in the part 1 we have done the entire formulation along with the initial and boundary conditions up to a point, but we have not looked at the specific boundary conditions or special terms that are applicable for the fusion welding. The formulation we gave was almost like for any liquid that would undergo fluid flow within the domain. So, we will look at those special terms that are applicable for welding now. The first thing that comes to our mind when we looked at the driving forces for the fluid flow that are happening in the weld pool is the thermal buoyancy, and that is basically the buoyancy effect due to the temperature differences within the domain. So, let us see what it looked like. So, basically the driving force because of the thermal buoyancy is coming from the density changes which are function of temperature. So, in other words density is going down as the temperature is going up, and because of density changes you would have combined with the gravity, you would have the resultant flow, and the flow is such that the liquid that is having lower density will go up as in away in the gravity direction opposite to the gravity, and the one which is heavy because of higher lower temperature that would be settling down. Okay. So, this is the kind of fluid flow that would be coming because of thermal buoyancy, and the way it is modeled in the equations that we have written is as follows. You basically have an assumption that is made, and I will just write the name for you here. The assumption is called a Boussinesq assumption. The reason why we need to make some assumption to combine the thermal buoyancy with the fluid flow equation that we wrote is because of an apparent clash between two assumptions. The first assumption we made is incompressible. Okay. Incompressible, we made an assumption that 1 by rho dou rho by dou t plus so the continuity equation that we wrote, we said that this can be changed as rate of dilation is 0. So, in this process what we have said is basically the material derivative of rho is 0, that is what we are saying basically. Okay. So, this implies that you should not have the density changing across the different control volumes taking into account the advection term, and that goes opposite in the phase of the density changing because of the temperature changes, and therefore, we must make an assumption that the density changes are only to lead to flow, but not to lead to the incompressible assumption being invalid. So, which means that this assumption is valid whenever the changes are less than 5%. Okay. So, in such situations you can 5 or maybe about 10% it is fine. So, for small changes in the density because of temperature variations, it is possible for you to make an assumption which goes by the name of Boussinesq assumption to say that incompressible fluid flow equations are still valid. Okay. So, under that constraint we can just then use the thermal buoyancy as a volumetric term. Okay. So, it is going as a volumetric term. Volumetric or the body force term, and which means that for the y component assuming that the gravity vector is along the y direction, for the y component you could then add a term which add a term which is going like this. Okay. This is the term that will be added to the equation. So, which means that we have f y minus dou p by dou y. So, in that you can add one more term like this. This is basically the reference temperature which would be usually the melting point itself, because the reference temperature above which you can take the differences and look at what would be the change in the temperature, and this is the compressibility. Okay, which is a property of the material, and this is the acceleration due to gravity, and this is the average density over the temperature ranges for which the melt flow is going to be experiencing the flow. So, by adding this term you basically have taken into account how the density changes are happening. You can actually see that beta into T into rho bar is nothing but this is somewhat like, okay, something like that. So, it is basically taking into account how the density changes are causing the fluid flow to come about, and thermal buoyancy is essentially taking the density changes coming because of the temperature differences in this manner. Okay. So, we can actually then by analogy see also if a solutal buoyancy can be looked at, and solutal buoyancy is quite straightforward. This term itself should be modified in the following manner. The density changes are because of solute or concentration differences and not the temperature differences is what distinguishes solutal buoyancy from thermal buoyancy. Okay. Other than that there is no other difference. Okay. And what does it mean? It means that this is going to be expressed as due to concentration differences. That is all. Okay. So, if you express delta rho as temperature differences, then you get the beta term that is coming up and the rho bar, but if you want you can express the change in the density due to the concentration differences in the location within the melt pool, and concentration differences are coming because concentration is a function of location within the melt pool. That is actually the situation when you have dissimilar welding or a weld pool in which you are adding a filler wire that is of different density. Okay, in such situations that is valid. Okay, so, solutal buoyancy and thermal buoyancy are both together as categories of buoyancy convection, which means that they are basically caused by the density differences within the melt pool acted upon by the gravity to lead to the flow. Okay. And how would the average magnitude look like? It would be for typical weld pool shapes about in the order of millimeters per second, which means that it is a very weak convection we are talking about. So, that is the reason why many of the models usually ignore the buoyancy term because it is very weak. Okay. We will see what is a strong term shortly, but millimeters per second or so is the kind of magnitude you will get. How did we arrive at that kind of a magnitude? That scaling analysis we will look at it in a small exercise as a part of the tutorials later on in this course. Okay. And the other driving force that would be playing a role in the case of welding for the melt pool convection is the thermal Marangoni. So, I will just call it as a Marangoni convection. Marangoni convection is basically caused by the surface tension differences as a function of the distance, and that can be understood by the following steps. Okay. So, step by step we can understand how it comes about. So, first thing that we must appreciate is that the surface tension, okay, solid this is the surface tension is from the liquid to the vapor. Okay. So, liquid vapor you can say. Okay. This surface tension is a function of a temperature which is very well known, because at boiling temperature the surface tension is not acting, all the atoms are escaping into the vapor readily. So, there is no surface tension acting, because surface tension is nothing but forces that are keeping the atoms in the liquid together bound to the rest of the bulk. Okay. So, therefore, you can imagine that the surface tension must be a function of temperature. So, how does it vary? So, usually it looks like that. You normally start the plot of a surface tension in the liquid domain with the x axis going from melting point, because below the melting point it is not liquid. So, you start from the melting point, and the way surface tension is going to change is from a high value it keeps going down. Okay. So, in other words, the temperature coefficient of the material, surface tension temperature coefficient is negative for pure metals. For pure metals, so that at temperatures close to the boiling point surface tension is negligible, it has gone to 0, and at melting point it is very high, because that is when the bonds are most active in keeping the liquid atoms bound to the rest of the bulk. So, this is the variation that we already know. Okay. How does this variation cause the fluid flow to take place in the weld pool is a question, and that will be illustrated now by drawing a small schematic on showing which part of the volume element of the surface is going to go in which direction. So, let us consider a schematic of the liquid pool and look at elements and see how the surface tension variation would be affected. So, let us look at this pool as follows. This is a liquid pool and rest of it is all solid, and together this is the workpiece. And in this, let us look at a plot, and we would then look at how the different plots are to be approximated. So, as a function of the distance, okay, let us first plot the temperature. Okay. So, how would the temperature look like when you go from the center of the pool away is something that we can plot, and that means that I am actually now looking at the topmost layer in this region. Okay. So, how does the temperature distribution look like? It looks like this. Here is a melting point. Okay. So, I am putting points here because that is what is defining the fusion zone end, and at the center of the pool you would have the temperature very high. So, you would have a peak temperature like this. So, you would have a temperature profile like that. Okay. So, that is the width of the fusion zone, as they can be seen also on the top. Okay. Now, this is how the temperature profile is going to look like: hot at the center, and as you go away the temperature is falling, and where it reaches the melting point, that is the melt pool width, and then further away it goes to even the ambient temperature, which is of the temperature of the solid far away from the center of the melt pool. And if this is how the temperature variation is, then how would the surface tension variation look like is something we can plot. Okay. You can see that as a function of distance, you can see that at the highest temperature, that is at high temperatures, you would have low sigma, and at low temperatures close to melting point we have high sigma, right. So, from that what we can do is that at high temperatures you have a small value, and at low temperatures you have a large value. So, which means that surface tension is going to look something that kind. Okay. So, it goes from a small value, it goes to high values away from here. So, which means that on the liquid melt pool, how does this kind of a surface tension difference is going to play a role in the flow is something that we can illustrate, and for that I would just draw the pool much bigger and then show you. Consider the elements like this, okay, at the center, and element here and an element here. Okay. Here you see that because the temperature is high, the surface tension is low. So, here it is low sigma, this is high sigma, then here also is high sigma. Okay. And the reason why the liquid in the melt pool is going to convect because of surface tension gradients is essentially to minimize the surface energy contribution from the whole surface, and the way it can minimize is by having more area which is having low surface tension, or high area, okay, more area, high area with low surface tension, or smaller area with high surface tension. Both ways the multiplication of surface tension with area can be minimized, which means that the way this should move is that if this can expand, this layer can expand, and if this can contract. So, then you achieve the surface tension contribution to the energy of the surface coming down, and this means that the direction of the flow is such that it goes like that, radially outward. Okay, radially outward, and the surface tension variation is only at the very surface of the liquid pool, and it does not have an effect on the entire pool. So, which means that this recirculation to close the loop to satisfy the continuity equation is going to happen inside, and it could be like this, okay, and it would penetrate to the entire depth or only at the surface depending upon the following situation. Okay. So, this convection penetrates more depth of pool if the viscosity is less for more depth. Okay, and you know already the viscosity is actually a function of temperature, which means that if the temperature variation of viscosity is not strong, okay, if it is weak function of temperature, then what happens is that at high temperatures the viscosity is less, and which means that you could have the pool entire convection will be in the depth of the pool. And in the case the viscosity is a strong function of temperature, it means that at high temperature it is less viscous, at low temperature it is more viscous, which means there is a viscosity gradient up, and that means that this liquid at the bottom is very viscous, it cannot be moved easily. So, then this surface convection will be limited to the top layer. Either way it is basically radially outward, and what does it mean by saying radially outward? It means that it would actually make the pool shallow and wide. Okay, so, that is the reason why, that is how it will be affected. So, Marangoni convection essentially leads to a melt pool which is shallow and wide, and the magnitude of the surface tension driven flow we can estimate it using a small scaling analysis, which I would discuss in a tutorial session later on, and that would come out to be about a meter per second. Okay, so, magnitude. Okay, so, in other words surface tension driven flow will be the strongest component of the velocity in a liquid pool, and it will be on the order of the meters per second, which should be actually slightly higher than the traverse rate of the torch, because traverse rate of a torch is generally about a couple of 100 mm per minute, or of that order, and that means that it is a very strong convection. The reason why it is such a strong convection is because of the strong change in the surface tension as a function of temperature, and temperature is also changing very dramatically with respect to the distance. So, coupled to that we will have this as the strong driving force. Now, there is a small modification in the way the fluid flow will take place when there is a solutal effect on this, and that is where we actually bring the idea of Solutal Marangoni. Okay, in what way it changes, I will try to redraw on this itself to show you the difference. Okay. So, what we mean by Solutal Marangoni is effect of solute elements on the Marangoni convection, so that the surface tension is not a function of only temperature, it is a function of composition also, and composition also are a function of distances in a particular manner. So, let us see what would be the effect. Solute effects, and particularly we let us take the effect of some surfactant elements such as oxygen or sulfur in steels. So, what these elements do is basically the following. These elements tend to go to the surface and segregate there, so that they can reduce the surface tension. Okay. So, such elements which migrate to the surfaces readily are basically the surfactant elements. Some soluble elements, like for example nickel in liquid iron, for example, they do not behave like that. They will be in the substitutional positions wherever iron is there, and they will not segregate selectively to one boundary. However, let us say boron, sulfur, oxygen, etc., they will tend to migrate to the boundary and then segregate there, changing the composition locally, so that the surface tension is lowered. Okay. So, such elements if they are present, they are going to change the surface tension behavior of that particular liquid metal. And how does it change, in what way? So, that is given by this relationship. I will show you here. This for an alloy, for example, what happens is, very close to the melting point, the effect of the surfactant elements is very high, which means that they will reduce the surface tension significantly, but the reduction of surface tension is not effective as you increase the temperature. So, as you go further and further at higher temperatures, amount of reduction is not significant, and after some temperature it is not at all present. So, in other words, the plot would look like that, goes up and down. Okay. So, in other words, whenever there are surfactant elements, the surface tension at low temperatures close to the melting point goes up, and then at a peak value, after that it just keeps coming down. So, we could then say that the plot is going to look like that. Some T naught beyond which it goes up. So, which means that surface tension coefficient of temperature is not negative always. Okay, it is actually positive at low temperatures here. Okay, I say, and in this region negative at very high temperatures. So, in other words, the sign of the surface tension coefficient is going to change, and if that changes, then our argument that we were discussing here is going to also change, and that is because the temperature is actually changing. Okay. So, which means that this plot is going to be modified, and you can see that at high temperatures it is still low, and at low temperatures again it is low, but it is going to be so you have got at T naught, the distance corresponding to the T naught is where the surface tension is maximum, and so on. So, this kind of a variation would immediately change the way the fluid flow is happening. For the same logic, what we do is as follows, it would change in the following manner. So, you see that at the peak temperature, at very high temperatures it is low, and at very low temperatures again it is low, and here it is high. So, you have a situation where you want to expand, but this wants to this also wants to expand, and here wants to contract. So, in other words, you now see that you have two loops, okay, and if you want to rotate it around, then you would have, so you have radially away, and this is radially inward. Okay. So, you would see that at the center it is away, but in the ends it is inward. Okay. So, this inward flow at the ends, this way inward flow at the ends is going to basically make the pool not very wide, but slightly narrow. So, which means that the flow is going to be like this, flow near edges of pool is inward, which implies that the pool is deep and narrow. So, in other words, if I want to superpose that kind of a change over this pool shape, then you would look more like this. Because of the heat going inwards, so the pool must be narrower, and it is also experimentally observed that in steels that contain surfactant elements like sulfur and oxygen, the same GTAW with everything all the parameters same for the weld pool, the weld pool is known to be slightly deeper and narrow compared to when it is not having those kind of an elements. Okay. So, this is how the surface tension is going to change the weld pool shape, and we can rationalize that from the surface tension variation. Okay. And Solutal effects are not playing a role only from the surfactant elements, it is a playing role also from the normal alloying elements, because the alloying elements also can, for example, change the surface tension in the case of dissimilar metals. So, one has to always pay attention to how the surface tension is changing as a function of composition, if composition changing as a function of distance. So, that ultimately we have to inspect whether surface tension is changing as a function of distance. The moment it changes as a function of distance, then immediately you start seeing the flow coming because of that variation. So, this is how the Solutal Marangoni convection is going to play a role. Okay. And let me just erase it so that we can come to the end of this lecture with some more body force effects. So, the other body force that is going to play a role in the convection is the electromagnetic force, Lorentz force. So, electromagnetic force is going to be given as, so the current density vector J and the magnetic field induced by the current itself, okay. And this can be calculated, and you can see that this is basically a force which is going into the Navier-Stokes equation in the body force term. So, simply you can add this into the body force term, and you need to calculate the current density vector in the entire domain separately, find out what is the force that is acted upon the liquid, and add that force to the respective body force terms, and that will also basically play a role in the convection of the pool. And you can see that convection of the pool is dependent upon the current density vector, and current can be going inward or outward depending upon the polarity. So, changing the polarity also means that we are going to change the way the convection is going to happen in the melt pool because of the Lorentz force that is acting. Okay. So, this is a body force term. Okay. So, let us just then look at a map of all the terms that we have done till now, and for which process which of the special terms are going to be effective. Let us just do that as a map by making a tabular fashion, which we did in the beginning of this session. So, the first term is the buoyancy term. So, let us take the thermal buoyancy. Thermal buoyancy is going to be given as a body force term, which means that it is going to come into the equation itself as an additional term. So, which means that if you were to look at a formulation of the fluid flow modeling in any paper, then you can look at the equation that they are solving, and you should be able to see the body force term there. Okay. And if it is there, that means that they are taking into account the thermal buoyancy. And what processes is it relevant? Actually, any process that is happening on earth where the acceleration due to gravity is present, then this term should be valid. Okay. It must be present everywhere. But we must pay attention that most of the times the welding is done in a flat geometry, so that the highest temperature is on the top and the gravity is actually downwards. Okay. So, in other words, when you change the geometry from flat geometry to overhead, the buoyancy convection is going to play a role. Okay. It is not acting in the same direction. So, pay attention to the geometry, but otherwise it is everywhere effective. But everywhere effective, but negligible in the sense compared to negligible compared to the Marangoni convection, but it is present everywhere and it is strongly affected by the geometry. Okay. The Solutal buoyancy is also a body force term, but it is only to be taken into account when there is a solute change that is present, which means that concentration changes are to be there, which means that in the case of, let us say, autogeneous or homogeneous filler welds not present. So, that is, if you do not have any filler and if you are going to weld the material using autogeneous welding, then there is no concentration differences that are happening, and therefore, there is no solutal buoyancy. and if you are also doing to do a welding with filler, but the filler is actually homogeneous filler, which means the same material as the base material, then again there is no concentration changes and therefore there is no solutal buoyancy. In the dissimilar welding it is very strongly present because there is a strong composition change across the melt pool, and in the situations where the filler is added which is different from the base material, again it is present. So, it is not present in autogeneous and homogeneous, and it is present in rest of the situations. And in the dissimilar welding, I would say dissimilar welding it is important. Okay. Now, what about Marangoni? Marangoni term, as you can see, is because of the surface tension change, and that means there must be a surface that is available, and the surface is available normally, and this is actually a surface boundary condition. Unlike the remaining terms, it is not appearing in the equation, it is appearing as a boundary condition, and it is present in every situation where there is a free surface available. Are there situations where there is no free surface? For example, let us take arc welding when there is a flux. So, the surface of the liquid metal is covered by a flux, it is not exposed to the vapor directly. So, therefore, the surface tension that is relevant is the surface tension between liquid metal and the liquid flux, and that surface tension is not a strong function of temperature. So, which means that whenever the liquid melt pool is covered by a flux completely and there is no free surface of the liquid metal exposed, then you can say that the Marangoni convection is very much suppressed and not very strongly present, and which means that if you have flux implies not strong, and it is very strong, for example, in materials which are being welded where the temperature changes are very drastically changing from the center to the edge of the pool. For example, laser welding and electron beam welding, the peak temperature is very high, and as you go in a small distance in a small melt pool, the temperature drastically comes to the fusion zone temperature, which is the melting point temperature. So, which means that you basically have these effects very strong in LBW or EBW, simply because the gradients are strong. Okay. And what about the electromagnetic force, and that is also a body force term, and naturally the electromagnetic force term should not be present when there is no electromagnetic force due to the process itself. That is, if it is an arc weld you will have that force, but it is a laser weld, it is not there. So, you can say that in laser beam welding it is absent, and in every arc welding it is present. Okay. And it depends upon the polarity also. Okay. So, as you can see that the different driving forces are to be kept in mind, and depending upon the welding process you must choose which of these are active, and you may see that some are boundary conditions, some are body force terms which come in the equation, and then some can be neglected in some conditions and some cannot be, etc. So, that way you can actually see that not all are used in every situation, and one must pay attention to the process conditions to pick the right kind of a term for the fluid flow. Okay. So, with this we basically summarize by also telling what we did not look at. So, let us just scribble those words what we did not look at. So, these are only for the research interest, mainly because some of you may want to further go into the research of these subjects. So, what is it that we did not look at? Rippling. Okay. So, surface ripples are known in welds. Okay. Normally a good weld with a what is called the good weld appeal is going to look like that, and each of these are basically arc shaped surface undulations which are supposed to be very uniformly spaced for a good weld, and this surface rippling is basically due to the free surface deformation. And that is not considered till now, and there are ways to model it. We will come to it if there is a required interest among the participants, and there are other things that we have not considered, for example, vaporization. Vaporization we would look at it briefly when when we discuss the conduction mode to the keyhole mode, but otherwise we are not looking at so called Knudsen layer vaporization and the related effects. We have also not looked at the effect due to the nozzles on the flow, that is the gas flow coming from the nozzles to protect the layer is going to affect the liquid flow. We did not consider. It can be dumped into the surface boundary condition if necessary, but otherwise we have not considered. Okay. So, like this there are some effects that we need to keep an eye on to know whether they are important in the process, otherwise we need to consider. Okay. So, with that I would summarize by closing the formulation. The formulation can be closed as saying that a Navier-Stokes equation plus, we can say like this, the formulation is closed like this. Navier-Stokes equation plus continuity plus special terms which are like this coming plus the boundary conditions which are basically, in the case of Marangoni you have got a special boundary condition, otherwise no flow condition or rigid body condition or no slip condition, etc. they can be the boundary condition, and then you have the initial conditions which are simple because initially everything is at 0. Okay. And you have got special terms also to take into account single domain approach, the terms that are required to make it a single domain. So, this entire thing now is enough for us to go ahead and solve the problem for the fluid flow in a melt pool. Okay. So, I will briefly discuss later on how to go about solving or what kind of software are able to solve this for you, etc. And we need to always keep an eye on what all goes in and how much can then be expected to come out. Okay. So, with this we close the fluid flow modeling lesson, and we would discuss further on the solutions in a later lesson. Okay. Thank you.